Welcome back to the deep dive. If you're spending any time really engaging with modern technology, you've definitely run headfirst into these big buzzwords, AI, machine learning or ML, and deep learning, DL.
They're everywhere now.
Absolutely. There are the engines driving, well, everything from those video recommendations you get on your phone to the surprisingly complex chatbots people are interacting with. But what's the real story here? What is the distinct relationship between these three? Are they just different words for the same thing, or is there like a clear structure, a hierarchy?
That's a key question.
And maybe more fundamentally, how does a machine actually learn anything? That's what we're tackling today. We're aiming to give you a clear, detailed, but also, simple explanation of this whole tech stack and how machine learning works, based entirely on the sources provided. We want to be thorough, not gloss over the important bits.
Yeah, and that hierarchy is really the best place to start. It's essential. People often use AI very broadly. It's the big umbrella term, right? The overall goal of creating machines that can sort of mimic human thinking, human cognitive functions.
Okay, the grand vision.
Exactly. But machine learning, ML, that's actually a specific way of achieving AI. It's definitely a subset of AI, not the same thing.
Okay. So AI is the destination,
Yeah.
maybe, and ML is one of the main roads we're using to get there now.
That's a great way to put it. ML specifically focuses on algorithms that learn patterns directly from data. Lots of data, usually. We call it training data.
Right.
The whole point is that the model, after training, can make accurate predictions or decisions about new data it hasn't seen before. It achieves this pattern recognition without a programmer sitting there writing out every single rule, like endless if-then statements.
So the machine itself is kind of figuring out the rules from the examples.
Yeah.
Okay. So where does deep learning, DL, fit into this picture?
Deep learning is where things get, well, really interesting and powerful lately. DL is a subset of ML. So AI is the biggest circle, ML is inside that, and DL is inside ML.
Got it. Nested dolls.
Pretty much. What makes DL special is its use of neural networks with many layers. That's where the deep comes from. Multiple layers stacked on top of each other.
Okay.
And here's the critical difference. With traditional ML, human experts often had to manually figure out what features in the data were important, like telling the machine, look at the corners, or measure the texture.
Feature engineering, they call it.
Exactly, feature engineering. Deep learning does automatic feature extraction. You can feed a DL model raw data, like image pixels, and it figures out the important features itself hierarchically. The first layer might learn to detect simple edges, the next layer combines edges to find corners, the next finds shapes, and so on, up to complex objects. It learns these relevant representations all on its own.
Okay, that's huge.
It is. It's basically ML, but scaled up in complexity and capability, which lets it tackle really messy, raw, real-world data much more effectively than older methods.
That idea, automatic feature extraction, that really clicks. It explains why DL suddenly took off for things like understanding images or speech, right?
Precisely.
Now, because we're going pretty long in detail today, aiming for that really thorough understanding, we definitely want to hear from you. What parts of this deep dive are standing out? Or maybe what concepts do you want us to explore even more next time? Let us know your thoughts and suggestions in the comments. Okay, so let's unpack the core process then. If the machine's learning patterns, how does that learning actually happen day to day, or rather in the development phase? What's the workflow look like?
Right, so the main idea in machine learning centers on optimizing the machine's performance on some task using a specific data set. This first big heavy lifting stage is called model training.
Training. Okay.
During training, the machine gets exposed to, typically, enormous amounts of data. It constantly adjusts its internal settings, things called weights and biases in neural networks over and over again. It iterates, trying to minimize the errors it makes on the training data until its performance gets as good as possible.
It's like studying for a massive exam.
Kind of, yeah. And once that training, which can take days or even weeks on powerful computers, is done, you have a trained model, then it can be deployed.
Right, and that's where we shift from the expensive prep work to actually using it in the real world. This deployment part, that's AI inference, isn't it?
Exactly. Inference is the flip side of training. If training is the long, hard study session,
Writing the exam answers?
yeah, then inference is actually taking the test, but instantly. When we talk about AI inference, we're running that fully baked, trained model. You feed it new data, maybe a photo it's never seen, a new sentence to translate, a current stock price, and bang! It uses the patterns it learned to make a prediction or classify that input.
So training is the heavy, maybe one-time cost, and inference is the fast, scalable thing that happens like billions of times a second across the internet.
You got it. Training is slow and expensive. Inference needs to be fast and cheap, relatively speaking. And no matter how complex these models get, deep learning or otherwise, almost all machine learning falls into one of three main learning paradigms.
Paradigms. Okay, what are they?
First up, probably the most common, is supervised learning. Here, you train the model using labeled examples. You give it the input and the correct output, the ground truth.
Like flashcards for the machine.
Exactly like flashcards. If you're building that spam filter we mentioned, you feed it tons of emails already marked spam or not spam by humans. The model learns the difference by seeing the examples and the correct labels. It's supervised because a human essentially provided the answers for the training.
Okay, makes sense. Supervised uses the answer key. So the second one, unsupervised learning, must be different.
Totally different. Unsupervised learning works with completely unlabeled data. There's no answer key provided. The machine's job is just to look at the data and find interesting structures or patterns entirely on its own.
So it's more like exploring your detective work.
Yeah, that's a good analogy. It's used for tasks like grouping similar items together, that's called clustering, or simplifying complex data, which is dimensionality reduction, or even finding anomalies, like spotting a weird transaction that doesn't fit the usual pattern. We'll dig into those more.
Okay. And the third one, reinforcement learning. That sounds kind of like game playing.
It really does. Reinforcement learning, RL, is the most action-oriented. It learns by doing, essentially. It optimizes a strategy or a policy through trial and error, guided by rewards and penalties.
Like training a dog with treats.
Very much like that. You have an agent, the learner, interacting with an environment. The agent observes the state of the environment, chooses an action, and the environment responds with a reward if it was a good action or a penalty if it was bad. The agent's goal is to figure out a policy, what action to take in which state that maximizes its total reward over the long run. It's always doing this balancing act between exploration, trying new things to see if they work better, and exploitation, sticking with what it knows already works well.
Okay, that clarifies the three big buckets really well. Supervised learns from labeled examples. Unsupervised finds hidden patterns in unlabeled data. And reinforcement learns through trial, error, rewards, and penalties.
Exactly.
So let's dive a bit deeper into the supervised models first. You mentioned they handle different kinds of predictions.
Right. When the thing you want to predict is a continuous numerical value, a number that could be anything along a scale, you use regression models.
Like predicting a house price or temperature.
Perfect examples. Predicting the exact price, or the degrees Celsius tomorrow, or maybe the amount of sales next quarter. Those are regression tasks.
And I guess these aren't all just drawing straight lines through data points.
No, definitely not. The simplest form is linear regression, which does find the best straight line. But often relationships aren't linear, so you use more complex models like polynomial regression, which can fit curves to capture, say, growth that speeds up and then slows down.
Okay, so regression handles the continuous numbers.
Yeah.
What if the output we need is a distinct category or a label, not a number on a scale?
Then you switch gears to classification models. Their job is to predict a discrete class, a specific category label. We see these everywhere.
Like the spam filter again.
Yeah.
Spam or not spam.
Exactly. That's the simplest type. Binary classification. Just two possible outcomes. Is this tumor malignant or benign? Will this customer click the ad or not? But you also have multi-class classification, where the model has to pick one category out of several options. Like identifying a handwritten digit, is it a 0, 1, 2, up to 9, or classifying a news article, sports, politics, tech, business.
And there's one more type.
Yeah, multi-label classification. This is where one input can belong to multiple categories at the same time. Think about tagging a photo. It could be labeled beach, sunset, and people all at once. The model needs to predict all relevant tags.
It feels like even these fundamental supervised methods are getting more sophisticated over time.
They absolutely are. And one big trend in modern supervised learning is using ensemble methods. That basically means training several different models and then combining their predictions. Usually the combined prediction is more accurate and reliable than any single model could manage on its own, like getting a second, third, and fourth opinion. Smart. Now, before we jump fully over to the unsupervised world, you mentioned something that kind of sits in between supervised and unsupervised, a way to be more efficient.
Ah, yes. Semi-supervised learning. It's a really clever approach, especially when getting labeled data is expensive or time-consuming, which it often is.
How does it work?
You start with a small amount of high-quality labeled data. You train a model on that first, but then you also use a much larger pool of unlabeled data. The model uses what it learned from the labeled set to help it make sense of and learn from the structure in the big unlabeled set. It boosts performance without needing tons of costly labels.
So you get more bang for your buck from the labels you do have.
Exactly. It helps bridge the gap and makes the whole process more scalable.
Okay, very useful. Now let's pivot to unsupervised learning. This is where the machine is really exploring on its own. How does it actually find meaningful structure in data when nobody's given it any answers? Right, so unsupervised learning primarily relies on two main families of algorithms. The first one we mentioned is clustering. The whole goal here is just grouping similar things together. The algorithm tries to make sure that items within a cluster are very similar to each other, and items in different clusters are quite distinct.
And how does it decide on the groups?
Well, one of the most common methods is k-means clustering. With k-means, you actually decide upfront how many clusters you want. Let's say you choose K4. The algorithm then randomly initializes 4 cluster centers, assigns each data point to its nearest center, recalculates the center based on the assigned points, and repeats this process: assign, recalculate, assign, recalculate, until the groups don't really change much anymore. They stabilize.
Can you give a practical example? Where would we use k-means?
Think about customer segmentation for marketing. You could feed the algorithm data about customer purchase history, maybe some demographics. You tell it, find me K5 distinct customer groups. The algorithm might come back with clusters representing, say, high-spending loyalists, infrequent big-ticket buyers, discount hunters, new customers, and maybe browsers who rarely buy. Suddenly, you understand your customer base much better and can tailor your marketing messages or offers to each specific group.
That makes sense. Finding hidden groups. What's the other main clustering type?
The other major one is hierarchical clustering. This approach is a bit different. Instead of picking K beforehand, it builds a hierarchy, like a tree diagram, often called a dendrogram.
How does it build the tree?
It usually starts with every single data point as its own tiny cluster. Then it finds the 2 closest clusters and merges them. Then it finds the next 2 closest clusters, which might include the one it just merged, and merges them. It keeps doing this step by step, merging the most similar groups until eventually everything is merged into one giant cluster.
See, this whole tree structure is showing how things group together at different levels of similarity.
Exactly. And then you can decide where to cut the tree to get the number of clusters you want. If you cut it near the top, you get a few large clusters. Cut it lower down, you get more smaller clusters.
Where is that useful?
It's great for things where you don't know the right number of clusters in advance or where the relationships are hierarchical. For instance, analyzing text data, like IT support tickets. You could cluster thousands of ticket descriptions. The hierarchy might show broad categories like hardware issues and software issues near the top. And then drilling down, you might see subclusters like laptop won't boot, password reset, VPN problem, software install request. It helps organize information and spot emerging trends.
Okay, so clustering finds groups. What's the second main family of unsupervised learning?
That's dimensionality reduction, often called DR. These algorithms are all about simplifying complex data. They try to represent the same essential information using fewer features or dimensions.
So reducing the number of columns in your data table, basically, but without losing the important stuff.
Precisely. The goal is to keep the meaningful characteristics, the core essence of the data, while getting rid of noise, redundancy, or less important variables. You're reducing complexity.
Why would you want to do that?
Several reasons. It's often crucial as a pre-processing step before feeding data into another machine learning model, especially if you have hundreds or thousands of features. Simply data can lead to faster training and sometimes even better model performance by removing distractions. It's also used for data compression, making large data sets smaller and, very importantly, for data visualization.
How does it help visualization?
Well, we can only easily visualize data in 2D or 3D. If your data has, say, 50 dimensions, you can't just plot it. But a DR technique, like the very common PCA, principal component analysis, or various types of encoders, can try to capture the most important variance in that 50-dimensional data within just 2 or 3 dimensions. Then you can plot it and hopefully see the underlying structure, like how clusters separate.
Okay, that makes sense. You compress the complexity down to something viewable. So we've now covered the classic foundations.
Yeah.
Supervised learning with regression and classification, unsupervised with clustering and dimensionality reduction, and reinforcement learning. These are really the workhorses, still powering a lot of AI today.
Absolutely. They underpin so much.
Let's try to connect this foundation to some of the really cutting-edge stuff people are talking about now. How would something like a self-driving car fit into this? You mentioned RL.
Yeah, the self-driving car is a fantastic example of complex reinforcement learning in action. The car's control system is the agent.
Okay.
Its state is its understanding of the world right now, built from combining data from GPS, cameras, LiDAR, radar, all its sensors, what's around it, where it is, how fast it's going.
And its actions.
The possible actions are pretty straightforward. Steer left, steer right, accelerate, brake,
Yeah.
maybe by varying degrees.
Right. And the rewards and penalties.
That's where it gets complex. The system is trained to maximize a reward function. It gets positive rewards for making smooth progress towards the destination, staying safely in its lane, maintaining appropriate speed, obeying traffic signal.
And penalties.
It gets penalties for things like jerky movements, sudden braking, getting too close to other cars, and obviously massive penalties for any kind of collision or traffic violation. Through millions of simulated miles and now real-world driving, the RL agent learns an optimal driving policy, the best action to take in any given state, without humans needing to explicitly program rules for every single possible traffic scenario.
Wow. It really is learning by doing with consequences. Okay, now for the elephant in the room. Large language models, LLMs, things like ChatGPT. How does all this foundational knowledge we've discussed connect to these massive AI systems?
It connects directly, absolutely. LLMs are typically built on an architecture called the transformer, which is a specific, relatively new type of neural network design that's incredibly effective for sequence data, like text.
Okay, a new architecture.
Right. But what does the transformer do? Fundamentally, it still relies on those core ML principles. Pattern recognition, learning from vast amounts of data during training, and then making predictions during inference. For LLMs, the main training task is often supervised, predicting the next word in a sentence given the preceding words. They learn the patterns of language from seeing billions of examples.
So it's still pattern matching, just on a mind-boggling scale with language. What makes the transformer special then?
The key innovation within the transformer is something called the attention mechanism. This allows the model, when generating or understanding text, to dynamically weigh the importance of different words in the input sequence, even words that are very far apart.
Ah, so it can track context over long distances.
Exactly. Older models struggled with long-range dependencies in text. Attention lets the transformer understand context much, much better, which is crucial for generating coherent and relevant language. So yes, it's still learning patterns via supervision, but the architecture allows it to learn exponentially more complex and nuanced patterns than before.
So the underlying principles haven't changed, but the scale of data and compute, plus architectural breakthroughs like attention, have unlocked this incredible new capability for understanding and generating human-like text.
You've nailed it. And what's really fascinating is how reinforcement learning has made a huge comeback in refining these LLMs. It's a technique called RLHF. Reinforcement learning with human feedback.
RLHF. How does that work?
So after the LLM is initially trained using supervised learning, predicting the next word, RLHF is used to fine-tune its behavior. Instead of it getting a reward for winning a game, the LLM generates several possible responses to a prompt. Human reviewers then look at these responses and rank them, or provide feedback on which ones are better, more helpful, more accurate, safer, less biased, etc.
The humans are providing the reward signal.
Exactly. This human feedback is used to train another model, a reward model, which learns to predict human preferences. Then, this reward model is used within an RL framework to further train the original LLM. The LLM gets rewarded for generating outputs that the reward model thinks humans would prefer.
Wow. So you're using RL not just to generate plausible text, but to steer the LLM towards generating text that aligns with human values and intentions.
Precisely. It moves the LLM from just being statistically accurate to being genuinely more helpful, harmless, and honest, according to human judgment. It's a powerful combination of supervised learning and reinforcement learning.
Okay, pulling this all together then,
Yeah.
what's the big picture takeaway? It sounds like all the buzz today around LLMs, generative AI, maybe even agentic AI, it's not some completely new magic. It's built squarely on these classic ML concepts we've discussed: regression, classification, clustering, RL, just massively scaled up and combined in new, really inventive ways using architectures like the transformer.
That's absolutely the key insight. This deep dive really shows that the intellectual foundations for today's most advanced AI systems were laid down decades ago. The core principles of teaching machines to learn patterns from data, whether supervised, unsupervised, or through reinforcement, remain constant.
It's almost comforting in a way.
It is. It confirms that human ingenuity just keeps finding incredibly powerful new ways to apply these fundamental ideas, enabled by more data and vastly more powerful computers. It suggests the limits aren't necessarily in the core theory, but in our ability to scale and architect the solutions.
That's a fantastic point to end on, and it raises a provocative thought, perhaps. If RLHF can use human feedback to align an LLM with our preferences for helpfulness or harmlessness, as these RL agents get even more sophisticated, could we potentially use similar reward mechanisms to teach them something far more abstract, like, say, empathy? Or does the nature of reward optimization fundamentally limit them to just finding the most efficient path, regardless of subtler human qualities? Something to think about. Well, we really hope this long, detailed, but hopefully simple explanation helped give you some of those aha moments, clarifying the distinctions between AI, ML, and DL, and shedding light on the core model types.
We covered a lot of ground.
We certainly did. If you found this deep dive valuable, please do give it a like. It really helps others find it. And we strongly encourage you to subscribe to the channel and make sure you activate that notification bell so you don't miss our next detailed analysis.
And please share this video with anyone else you think might benefit from these insights.
Absolutely. Thanks for joining us on the deep dive, and we'll see you next time.